is Alejandro, and welcome back for day 14 of me doing the NeetCode 150 challenge. So today we're doing yet another trees problem, and let's get straight into it. Okay, problem 110, balanced binary tree. LeetCode easy. Given a binary tree, determine if it is height balanced. Okay, a height balanced binary tree is a tree in which the depth of the two subtrees of every node. Okay, it's a binary tree in which the depth of the two subtrees of every node never differs by more than 1. Okay, so example 1. So here the output is true because, okay, the left has a height of 1 and this has a high or a max depth of 2, right? Okay. So this is kind of like AVL trees, right? Where it's like a tree is considered balanced if, yeah, like the two subtrees never differ by a height of more than 1. Okay, essentially we can just do what we did in like the last two problems, right? Where it's like we compute the depth of a tree, and then it's like, okay, between the left and the right, get their heights or their max depths, and that's pretty much it. I forget. Maybe I should rewatch the videos on AVL trees. If you don't know, AVL trees are essentially just like regular BSTs, except that you have like rotation algorithms and so on, so that you always keep the tree height balanced, right? But here we just want to return if the tree is balanced itself, right? So an easy way we can do what I did last time, which is like I cache the results in a hash map for each node, like its height and so on. Then I just traverse through all the nodes and make sure that they're all like height balanced. Right. I could also, I could do something like that. I want to see if I can challenge myself, because I remember the last problem, NeetCode was able to, kind of like do that 2 birds in 1 stone kind of trick by like having the return value being like, like the height of the tree itself, and then it's like, return of the left. I wonder if we could do something like that. Okay, first of all, we can do it my way, right? Which would be something like this. Self dot, or you know what, we can make a function like called get height, right? Def get height, or like get height, get max depth, same thing, given a node, right? And here we'll have a def init self dot node to height is equal to an empty hash map, right? So here we'll do if node in self dot heights, node to height, tree node to height. If node in self dot heights, return self dot heights of node. Otherwise, we want if not node, return 0. And then we'll do it's gonna be the max of the left and the right plus 1, right? So return 1 plus max of self dot get height of node dot left, as well, of self dot get height of node dot right? That's essentially the height, right? So now that we have a function for getting the heights efficiently of every node, it's like, okay, if not root, return true, right? It's just balanced. Left height is equal to self dot get height of root dot left. Right height is equal to self dot get height of root dot right. And then we do like diff is equal to absolute value of left height minus right height, or you know what, if diff is greater than 1, then return false. Otherwise, this is just for this, right? So it's like, okay, the left subtree has a height of 1, this has a height of 2, and it's like, okay, return here we know that it's true, right? But let's say that this node 15 wasn't in there, right? So we just have 9, 3, 20, and 7. It's like, oh my goodness, the height here is 2 and the height here is 1. They differ by at most 1, therefore it's good, right? But then it's like, or let's say like, this had another node and another node here, right? So if we have something like, we have 3 here, we have that 9 here, and then we have a 1 here, right? But then here I have my 20, and my 7, and my, let's just say 5, right? So here's like the height on the left here, right? So 9 and 1 here is a height of 2, and then 27 and 5 here is a height of 3, right? And so 2 minus 3 absolute valued is not greater than 1, right? So that it doesn't differ by more than 1. So from here, it's like, okay, we're good, right? But we can't just return true, because if we look at this right subtree here, then kind of like, you know, in AVL trees, you'll notice that this one is like right heavy, right? So this one's height, well, it has nothing on the left subtree, so that has a height of 0. And on the right subtree, this has a height of 2. 2 minus 0 absolute valued is definitely greater than 1, therefore this is not a balanced tree. So we additionally also have to check, like, okay, is return, you know, that both the trees are high, right? So return self.isBalanced root.left, and that self.isBalanced root.right, right? So now we have essentially checked, okay, from the root node, the 2 subtrees below me do not differ by a height of more than 1, right? Now, for both of these subtrees, I need to make sure that they are also recursively balanced. Otherwise, I know that I must that I must not have a balanced tree. And this honestly makes me kind of curious. I want to relearn how to implement AVL trees. So I remember I learned AVL trees really well. It was back. Okay, first of all, let's submit this. Let's run this before I just keep yapping. There we go. Let's just submit. And there we go, beautiful, beat 78% and so on, We can also figure out if we can do a more efficient way where I don't have to do the get heights like this. But one thing I was saying is that I kind of want to restudy how to solve AVL trees. I remember in the University of Toronto, it was my a second year course where we're learning an introduction to, like, you know, common data structures and some algorithms. Really, the algorithms wasn't like the advanced algorithms course. And I did not understand at all the way that the professor was teaching AVL trees. And I was just shaking my head like, what is going on in that class? And then I remember I watched that an MIT courseware video on AVL trees, and so I think it was by Professor Eric Dermain. It was just like, you know, 40 minutes. Like my professor at U of T like had spent like, I think, like, you know, maybe 2 to 3 weeks just covering AVL trees, right? And then or probably max 2 if not 1, right? But like at least 2 lectures if not 3, or maybe 4. And probably, yeah, okay, but more, I think like 2 lectures and maybe 3. But Eric Dermain, I saw that MIT open courseware videos on AVL trees, like I think it was like 40 minutes or 45 minutes or something like that, and boom, instantly clicked, understand AVL trees, understand how to do rotations, absolutely everything makes sense, and so on. And I was just going inside the lectures like, oh yeah, this makes sense, this makes sense, this makes sense, this makes sense. So always leverage online open source material whenever you can, because honestly they're even better than what's taught in schools and so on, which is kind of a shame, but like so I'll probably do a little bit of studying in my own time to kind of remember how to re-implement AVL trees and so on. And I say this also because there was one LeetCode daily problem, so not in this NeetCode 150 series, but there's one of the LeetCode dailies for the other series that I'm doing, where I solve the LeetCode daily problem every day. So here you see the streak of 81, and and one of the problems I was like, oh, I should use a binary search tree, but then I was like, no, I shouldn't, because that'll be an worst case O of n, because I have to like keep inserting, and let's say I keep inserting to the right. But obviously if I use an AVL tree, then I would have everything to be that log n property, and I could have done things efficiently and so on. So you know what, after this video in my own time, I might just go rewatch that MIT video, or there's probably some video by Abdul Bari on YouTube on AVL trees and so on. So I might watch one or both if they both exist and so on, just because that's a neat little data structure. And again, the reason I'm talking about those, by the way, is because AVL trees are essentially BSTs where you always force the tree to have this height balance property, right? So it's not some, like with a regular BST, what's the problem is that you might always add nodes to the right, and you might actually end up with a linked list instead of an actually, like, you know, balanced binary search tree that most people think about, right? With an AVL tree, it's like, you know, there's a little bit more steps involved and so on with the rotations and so on. But again, whenever you insert a node, delete a node and so on, you'll always ensure that the tree itself is height balanced, and so that way it's like you can always rely on the, you know, like log n complexity for, like, you know, searching, adding and deletion and so on. So it's just very, very, very nice and convenient in that way. But otherwise, okay, let's try to see if we can make this a little bit better, because obviously here we're using a get height function. can we do this all inside this one function and so on? Even though this is efficient and, you know, we almost pass more than 80%, let's see if we can do a little bit better, right? So here the point is that I get the height of the left and right subtrees, right? So if I can make this function return the height, right? So what if I make this function return the height, right? So, yeah, I can do something like this, right? So is balanced, we'll say this function returns height of root. Oh, I can't do this, right? Because we need to return true, right? But okay, maybe I can do it without at least using O of n memory. Right. So I need another function here, right? So def. So I really just need that get height function. Would return the height. I could also do something that similar to what NeetCode did with, like, you know, that non-local variable stuff, but I don't get that stuff too much. Okay, I'm trying to think. Can we do this a little bit more cool, let's say, right? So if this function returned the height, but again, that's what I'm doing here, right? The other idea is like, okay, what if we don't use, you know, O of n memory? So that would essentially be an improvement. I don't think we can do this without at least using another function, because this needs to return a boolean, but we need to be able to, like, you know, reliably have things heights. But at least we can maybe just say, okay, maybe I do def. So here maybe I do a self dot res. I initially say is it equal to true, right? Is balanced, or self dot get height, right? So this is a new one, right? Self root and update res, right? So here I can do something like, okay, I just got to think about this, right? So this solution is a clever one and so on, and I'll do an explanation of how I was able to solve the problem in the end, but I just want to challenge myself. So like, okay, right now we have an O of n solution with O of n memory, but can we do it without using that O of n memory, right? So if not root, then return a height of 0, right? Otherwise, left, so this will be the same, right? So bada bing, bada boom, and it'll be this instead of that. So yeah, there we go. And here we will return 1 plus max of left height and right height, right? But the point here now is that we want to update our res variable, right? So now we have access to the left and right heights. So here, yeah, so we're not going to return res or so on. We're always going to return the heights. That's the point, right? So first of all, here we're just going to say, we're going to do the same thing, right? So diff is equal to the absolute value difference of these two. So yeah, we might as well just do this. If diff is greater than 1, and then here we're going to say self.res is equal to false, right? And then return this. So now we have a get height and update res. So here we're going to do return self.res. If not root, return self.res. We initialize self.res to be equal to true. Right? Or here I can just write another def is balanced with the same stuff. Right? And then this I will just comment out for now. So if not root, return self.res. Or not self.res. Right, if self.res is false, So if we've already found that it's false at some point, we always want to return false, so we want to essentially end our recursive solution as quickly as possible, right? So here we want to do, I'm trying to think. Self.get height date res. And here we just return self.res actually, right? Okay, so first of all, does something like this work? I misspelled that. Is balanced. Oh, it does work. Okay, so we can submit this. Aha. Okay, and now we can also make another optimization, or self.res is equal to false, right? So let's just make it like this, right? So this makes sense, right? We need to terminate early. Or I can do if or not self.res, but I think this just makes it explicitly clear. If my self.res is false, then just don't care what the heights I return, right? Just return 0, 0, 0, 0, 0, 0, and the execution context as quickly as possible. And then I come back here and return self.res, right? At any point, if I figure out that my solution is false, just get out of there, right? Do not keep computing the left and right subtrees and so on. Just end off as quickly as possible, right? It's still like, you know, the same asymptotic complexity. It's just like at any point, if I realize like, oh, this subtree here is definitely invalid, then okay, just return quickly, right? So here I can submit something like this as well. So yeah, so okay, again, the times are a bit more random and so on, but like this makes things a little bit more efficient. And I actually like this. You know what? This is a little nicer than my get height function. Or at least it should be faster. So now I don't use O of n memory, I use O of 1 memory. Okay, very, very cool. Here we have a get height function. We don't need this guy anymore. Self.res is equal to true. Or you know what, you can call self.res and call this self.isBalanced. We'll just keep it equals equals false. If self.isBalanced is already false, then end execution context as quickly as possible, since answer will be false no matter what. Still be false. Right? Although here I've deleted my isBalanced function. Whoops. Okay, let's make sure I don't delete that. So let's come back to when I had my isBalanced. Whoops, that was a mistake. Okay, so I definitely want to get rid of this guy. Then the rest here I definitely don't want to get rid of. Okay, def isBalanced. There we go. We can even move this guy up here. Right, and then just get rid of these one lines right here. Self.isBalanced, yep. So this just returns self.isBalanced. And there we go. Just run this one more time. There we go. Passes. And there we go. Bada bing, bada boom. So 45% and so on. Seems like we might be a little stuck, but again, it's just like we differ by a couple milliseconds. So if we resubmit a couple times, you know, over and over, we might end up getting to the point where it's just like, okay, maybe we're a little slow. Maybe it's just like, you know, if we get rid of this, then it's like it's a little bit faster. I don't expect it to be. But yeah, okay, it's just like, it just values, you know, like, oh, you're doing this extra little ifs check every single time. That's annoying, blah, blah, blah. I wonder, I could also say self.isBalanced. Yeah. Again, it's just like, technically this should only make things faster, right? It's just like the fact that you have to make that additional, like, check of like, is this false or true every single time, that can make things a bit slower. But like usually with very, very, very big trees, like this should only be able to make things faster, right? Okay, and there we go, 97%, just very, very nice. So again, it's just it just matters a little bit because the solutions are so close in terms of milliseconds and so on that it's like, it looks like you're between like 15 and 97% and so on, but this is an optimal solution. But okay, as always in all my videos, I do a quick recap of how I was able to solve the problem. So for this problem, we were tasked with the task of finding whether the balance tree is height balanced. So this is very similar to AVL trees, where again a tree is considered height balanced if between the left and right subtree of every single node, those heights differ by only at most one, right? So anything is allowed to be a little bit right heavy or a little bit left heavy, but by no more than one, right? And it's like left and right heaviness, like, depends on the heights of the left and right subtrees of every single node, right? So in this case, for example, this binary tree is balanced because from this root node of 3, the left subtree here has a height of 1, and the right subtree here has a height of 2, right? So this this is balanced, and then this subtree is also balanced, and this subtree is also balanced. This one is also balanced. This one is also balanced. So every single node has that quote-unquote balanced property, where for a node, that node is considered balanced if the left and right subtrees of that node differ by a height of at most 1, right? And a none, like for example, the left subtree of 9 is none, so that has a height of 0. The right subtree is none, so that has a height of 0. So 0 and 0, those differ by at most 1, right? And so the idea here is essentially I create a new function called getHeight and update. Maybe I should call this getHeight. Let's just call this getHeight, or getHeight and update res. Right. The point of this function is that essentially I have this global variable here called self.isBalanced that is initialized to be to true, right? So for now it's like I've not been disproven. I believe that this binary tree is balanced, and I will believe this until I am proven wrong, right? Or otherwise I traverse the whole tree and I still have found that it is balanced, right? So I initialize to true, and I'm an optimistic person, and until I'm proven wrong, I'm convinced that this binary tree is balanced, right? And so essentially here, all I do is I run this getHeight function and return whether the tree is balanced or not, right? And so what is this magic getHeight function? Essentially here, whenever for each node, I'm essentially going to get its height, right? So this function returns the height of a node, right? So for example, 3 has a height of 3, right? Because like the left subtree has a height of 1, the right subtree has a height of 2, right? And so the height will always be the maximum height between the left and right subtree plus 1, right? So 3, since this is the subtree with the higher height of 2, this node 3 will have a height of 2 plus 1 is equal to 3, right? And so this function, essentially all it does is it returns the height of a node, right? But also, in order to get the height of a node, you need the height of the left subtree and the height of the right subtree, right? And what you're going to do here essentially is say like, okay, I'm going to compute that left and right subtree heights, right? And then return like the maximum of those two heights and plus 1, right? Because it's the height of my actual node. But I will add a little step in there that says like, okay, what is the difference in height between my left and right subtrees, right? So I take the absolute value of their subtracted heights, and if I see that the difference is greater than 1, i.e. their heights differ by more than 1, then I will give my self.isBalanced property. I will say that this is false, right? The tree is now permanently, like this is now permanently false because I have noticed that this tree is not balanced. And what's nice is inside of this getHeight function, I also say like, oh, if it is not the case that the tree is balanced, right? If I have ever set this to false and so on, I will keep returning 0, so to just finish like this function as quick as possible, because I don't care about getting the heights of the remaining nodes or whatever and so on, because I already know that my solution is false, right? I have found at least one part of the tree that is imbalanced, therefore the entire tree cannot be balanced, and so I will just return false up here. So that's why I have this little check where it's just like, okay, if I have already found that this tree is not balanced, I'm just going to keep returning 0, even though that's not the actual height of the root node and so on, because I just want to get rid of this get out of here as quickly as possible and just return a false here at the end, right? But otherwise, if I've never set this the case and so on, I'm just going to keep returning the heights of the trees until I get through every single node, and at that point I just return self to this balance. The very first time around that I solved this, so for reference, this is an O of n solution with O of 1 extra memory. The very first time that I solved this problem was with O of n time and O of n memory, but that one was a bit more intuitive. Essentially what I did is I wrote a helper method that gets me the height of every single tree, and I store a hash map or a Python dictionary that maps nodes in the tree to their height, right? And so I go through the entire tree and I populate each node with their height, and that way in my isBalance function I essentially said like, okay, let's go for every node. We already know the height of every node, so let's get the height of the left subtree and the right subtree. If their difference is by more than 1, then return false. Otherwise, just keep going and so on until you've searched the whole tree, right? And so maybe that was a bit more intuitive way of understanding, but that solution required O of n memory because again I map every single node in the tree to its height, versus here, instead of using O of n memory, I'm using O of 1 memory. So it's just a little bit of a cleaner solution. I don't know if this problem has any follow-up, so let's check. Doesn't look like it, so that's pretty much it. As always, I'll come in here in the NeetCode 150 section just to check up that I did this problem. If you're curious about the remaining schedule and upload dates for the rest of the problems that I will be doing, I'll have it pinned down below in the comment section as a pinned comment. So again, like every single problem that I will be doing and the date that I will be solving that problem, including the ones that I've already solved, all down in the comment section as a pinned comment in case you are curious about that. But otherwise, that's pretty much it for this video. I hope that you found it useful and enjoyable, and if you did, I would highly appreciate if you left a like or a comment, and otherwise, I'll catch you in the next one. So until then, ciao ciao, my friend. Bye bye.